PS University. So my topic is SOC for image processing using SIFT Accelerator. So SOC, because all the components like input output ports and CPU and memory can be put onto a single chip. Then the algorithm SIFT stands for Scale Invariant Feature Transform. So it was introduced by Deloy. The algorithm is used for feature extraction from an image. So the application include object recognition, panorama and face recognition. So motivation is when on an image, if any points is considered to be as features, those features should be like stable. They should not change due to object position, illumination or scale. So the features cannot be the patches in the like the shadows in an image. Those cannot be taken as features. Then the feature should not change with object rotation or scale changes. Then this is this paper is the literature survey. This paper introduces SIFT algorithm completely, and they provide hardware accelerators for hardware for 2 steps of the SIFT algorithm, that is key point identification and feature descriptor generation. So these are the 4 steps of SIFT algorithm, which I will be explaining it in detail later. So in these 2 papers, in the first paper, the Gaussian kernels for filtering, it is done outside the hardware so that the computation costs are reduced. And in the second paper, the feature detection is only for 30 frames and the resolution is 9020 and across 1080. So the abstract is we have designed, implemented and generated IP for SIFT algorithm. Then the key points detected are tested for invariance with rotation and intensity changes. Then the algorithm can be applied for various kinds of or formats of the image with the different sizes also. So this is the block diagram where the input RGB image is connected to grayscale, then the Gaussian filtering happens, then key point detection, then magnitude orientation calculation and then feature description. The algorithm is implemented with conjunction with Vivado and MATLAB. So at that time we get a model composer blocks. So the pre-processing and post-processing blocks include the Xilinx blocks, and the model composer blocks does the actual algorithm work. So the first is Gaussian filtering. The Gaussian filtering has multiply, adder and shifter inside, with the input being the grayscale gray image and the output is the filtered image. So first, so these are the equations. For here we don't have any single Gaussian filtering image. On the image, the successive filtering is done. For that, the image is convolved with one Gaussian kernel. Then we get the Gaussian filtered image. So I said successive Gaussian filters. So the successive Gaussian filters are subtracted to obtain DOG. DOG is difference of Gaussians. So these are the equations. The general Gaussian equation does not have k sigma here. It is just sigma. So to get successive Gaussian filtered images, so we multiply the factor k, and the sigma is depicted with this equation. 1.6 is the standard number which is given by Deloy, the person who introduced SIFT. And we have 3 octaves. So the number of octaves means the group of successive Gaussian filtered images and difference of images together is called octave, and single set of Gaussian filtered images and DOG images is called pyramid. So when we go to next octave, the size of the image is halved. Like if the original size is 512 cross 512, it becomes 256 cross 256, and the third octave becomes 128 cross 128. So this is the convolution procedure. It's an example to understand convolution procedure. So this is actually a sober filter kernel which I have taken just for the example. So this kernel is inverted and the convolution happens like this. The pixels which are overlapped are multiplied and the results are added, and the result will be present in this particular part. So this is the kernel origin. So the result is present at the pixel where the origin sits. So this is the model of the first octave. So this is the input image. Then these are the 4 sets of Gaussian filtering. So the number of images in an octave and the number of octaves depends on the size of the image and its image quality. So this is the utilization estimates, and these are the outputs for the first octave with the sigma values, and to understand that there is a difference, I have displayed the pixels, and this is the difference of Gaussians. So the DOG gives the border of the image. So we can see that here almost in the third image of the first octave, all the borders are almost seen. So this is the second octave. So in the second octave, the border is finished here itself. Here you don't find any proper border. So in the third octave, the two, it appears almost black, but to show that there is an image, I have just done some transformations in the PPT itself. So for us, for this 512 cross 512 image and this quality of image, 3 octaves and 4 images per octave is fine. So the next step is key point detection. It's an example to understand key point detection. So these depicts 3 DOG images in an octave. So the every image, every pixel of the center DOG, the like example, the pixel depicted as 0 is compared with 8 pixels around it and 9 corresponding pixels in the above and below DOG. If this pixel is maxima or minima, it is taken as key point. Otherwise, it is neglected. So this is the model and utilization estimate. So this is the output of key point detection and the pixel value. So third step is magnitude and orientation, which is started by this equation. So this pixel minus this, like example for this pixel minus this pixel whole square and this pixel minus this pixel whole square gives the magnitude, and the ratio and tan inverse gives the orientation. So this is the model and utilization. So for the magnitude calculation gives the border, and this is done for every pixel in the Gaussian image, and this is the phase calculation also. So the next step is orientation of histogram. So the magnitude calculated in the previous step is plotted as histogram. So for that, 360 degree of a circle is divided into 36 bins, where each bin covers 10 degree. That means 7 intensity ranges, that is the 0 to 255. In that, each 10 degree covers 7 intensities. So the height of the histogram gives the that means the number of pixels falling into that range. Then this is the model and the utilization. Then the feature descriptor, the orientation what we calculated, that is like 360 degree of a circle is divided into 8 bins, where each bin covers 45 degree, that is the angle. Then and it is plotted like this on the pixels. This is on the each of the pixels. Now this pixel, there is 16 cross 16 area is taken, and they are converted into 4 cross 4 subblocks, and those arrows are combined, and we obtain some star like structure like this. This is the output and the expansion of them, a small part. Then this is the model and the utilization estimate. So I said the SFT is invariant with rotation and intensity changes. To check that, I have done 3 transformations. One is intensity reduce, increase and rotation. So this is to reduce the intensity, the image is divided by intensity reduction factor. So example I have taken as 5. So this is the intensity reduced image and key points detected on that, and key point matching what is that, I'll tell later. Then this is the intensity increased image, then key points detected in matched image. So image rotated by 90 degree, key points and match. So key point matching is this an example to understand. So the first one depicts the original image, the one which the SIFT algorithm has applied. Then this depicts the transformed image, the one may be intensity reduced, increased or rotated. So key point matching is every corresponding pixel are compared. So this is compared with this one, 2 is compared with 2, like that. If they are same, that particular place stores a 1. If they are different, like 5 and 6 is different, so that particular place stores 0. So this is the comparison. So for original image, the time for calculation is 0.84. So the time is almost less than a second. All these are in seconds. Then number of key points, these are number of key points detected in all those images. Then the number of match, percentage of match is around 99% on an average. So SFT is a better one. This is the whole block diagram and model composer. Then I have also tried this in system generator, Xilinx system generator. So this is the whole model. Here it's not visible, so I have expanded here. This part forms the image pre-processing, and these form the image post-processing. And this is the inside blocks, one of the part it is. So here the main octave 1 code stands, and these are the extra blocks for connecting them. So I said it is the algorithm can be applied to any image format, such as JPEG or PNG, BMP, any kind, and any image sizes. And the time for calculation is almost very less than a second, and the number of key points are also very more, around 1000 and 2000. So I have compared with the three papers what I have showed in the beginning. So the first paper used board NEOS 2, and there then time they have taken is around 2600 seconds. So it is around 2-3 minutes more than and minus 49 or 36 seconds in two boards I have tried, Xilinx 7000 and Kintex. So this is around 2% of the time what they have taken in this, and here it is the key point detection. But a different version minus this version, and 80, the that is 1000. Means 512 cross 512 itself it is almost 1000, and the time is very less. So even here my the model is better. So if I even double this, the key points will also get doubled. So conclusion, as I have already said, it is 2% of the paper in the algorithm, the time taken in the algorithm paper 1, and the kernels, and in the second paper the kernels I said it was calculated outside, but here everything is on the FPGA itself, and it is 99% matching is obtained. More and the future work is the image what I have given is from a file. So I can acquire them from a camera in the laptop or any that, and it can be used, the feature key points detected can be used for object detection and video processing. These are my references.